Hello everyone. It's difficult enough to find critical values of Z for Z testing when using tables, so I thought I'd put together a brief MP4 to show you the process in a little more detail than in the lecture notes. In the first step of the process, we determine what level of confidence we're going to use. Do you want to be 95% certain you're right? If so, we'll fix alpha at 0.05. If you'd like to be 99% certain you're right, we set alpha at 0.01. In the next step, you need to decide if you want to do a two-tailed test, in which case you're testing whether two items differ, or a one-tailed test, and in that test you would look at whether something is greater or less than another. For a specific example, suppose we're comparing the health of high school teachers and college professors. We could hypothesize that the health of college professors is different from that of high school teachers. Actually, the null hypothesis would be that the health is the same. So that's a two-tailed test. The health of college professors could either be greater or worse, better or worse than high school teachers. If we posited that the health of college professors is greater than high school teachers, that's a one-tailed test. And it matters in terms of using the z-tables. So in step 3, we fix the standards to determine the probability that the values in the tails are going to be significant. And in that sense, I mean significantly different. So if we're using a two-tailed test and we're fixing alpha at 0.05, we divide by 2 because half of our critical values go into each of the tails. So for that two-tailed test at 0.05 alpha, we're going to have 0.025 in each tail, or 2.5% of our distribution is going to be in each tail. So the critical area are values less than 2.5% and values greater than 97.5%. And if you're using a proportion table, it'll be less than 0.025 and greater than 0.975. If we're using a two-tailed test with alpha at 0.01, then we're going to have 0.005 or 0.5% in each tail. So the critical area is going to be the area less than 0.5% and greater than 99.5%. Again, if you're using proportions, it'll be the area less than 0.005 and greater than 0.995. If we're doing a one-tailed test at 0.05, the area will be greater than 0.95 or 95%. And at the negative end, it will be less than 0.05 or less than 5%. For alpha of 0.01 in a one-tailed test, the value will be greater than 0.99 or 99% and less than 0.01 or 1%. That's for one tail. In the fourth step, we decide which z-table we're going to use. And then we determine if it's proportions or percentages, what the values are for Z. The PDF table is proportions and Monroe is in percents. So in step 5, we use the Z table, and I'm going to follow through on both the PDF form and the Monroe form. The PDF, for the PDF, we want to find the lower end proportion, and that's values less than 0.025. So let's pull up the PDF. Here we are. And so this normal distribution here shows the area, critical area, that we're going to try to find a Z value for. And when we're finding a Z value, we're looking for the number of standard deviations from the mean. So we look up 0.025 and read across that's minus 1.9, and then read up 0.06 we add to minus 1.9, or subtract it technically. So our z-value for the small end is minus 1.96. At the upper end, that's the second page of the table, we're looking at z-values for an area greater, and so we're looking for 0.975, which we find here, and sure enough, it's positive 1.9 and reading up 6. So areas less than minus 1.96 and greater than 1.96, we will conclude are significantly different values than the mean. 1.96 standard deviations away. Should I do this for 0.01? Okay. So we're going to look up 0.005. And we find 0.005 right between these two values. And so it's minus 2.5, and this column is 0.08. So minus 2.58 for the lower critical value. And are we going to find the same thing for positive? Yes, indeed, because if we look right here, you'll see that 0.995 falls at plus 2.5, and the nearest column is 8. So that's how we use the PDF form with probabilities, well, proportions, and I guess one comment I would make is that 0.05 and 0.01 are so common that you might as well just memorize the z-values for them, since people use them a lot. Now, Monroe is a little harder to use. It's a percentage table, so we're going to have 2.5% of our distribution in each tail for alpha at 0.05. The tails will be for values less than 2.5% and greater than 97.5%. The twist for Monroe is that it's only half a table. So for the high-end value, you're going to need to subtract 50 from your high-end percentage, and this gives us 47.5 for the high-end value. And if we go to Monroe, and I know these are really hard to see, but if you squint pretty good here, you can see 47.5 right here, and that's the 1.9 row, and that's 0, 1, 2, 3, 4, 5, 6, and this is the 0.06 column. So it's the same result that we found when we used the PDF. And for the low end, we subtract 2.5% from 50% to get 47.5 again, and we read the row and column values and make them negative. Or you can just take your 1.96, since you now know that the negative end will be the same thing with a negative sign, and come to that conclusion. If we do 0.01 alpha in Monroe, we're going to subtract 50 from 99.5 to get 49.5%. And so we go to Monroe, and it's the second page of the Monroe table, and Right here we're at 49.5%. It's row 2.5 and column 0.08. So it's the same result, a different table. In the end analysis, if you're having trouble using the tables, you might also go online and you can probably find a lookup table where you can just enter your alpha and they'll tell you the z-values. I hope this was helpful. Please let me know if you have any comments or questions.